session of Orion Uncovered here from Leiden. We had an introduction at the beginning of the first session. So welcome back with some coffee and cookies here. We traditionally start with either an audio or a video problem, but I hope that everything is all right now, and we will head straight into the next talk by Sarah Rezai and Chalmers on the connection between Orion A and Kappa Orionis. So please go ahead.
Thank you. So hello everyone, I'm Sarah Rezai Khoshbakht and I'm a postdoc fellow currently at Chalmers. I work on the 3D mapping of the dust in the Milky Way, and in particular I will tell you about the work I've been doing on Orion, and this is in collaboration with Corinne Byler-Jones and Juan Soler at MPIA. So why do we care about 3D dust mapping? Actually, studying the dust in 3D can tell us a lot about different information. In particular, if we know the distribution of dust in the 3 dimension, that allows us to study the star-forming regions like Orion, for example, and also like larger scale structures like the galactic structures and the spiral arms of the Milky Way. So before I proceed further, I want to make some points more clear. Namely, the difference between the extinction and dust density. These terms can sometimes be like exchanged, which is all right, but it's clear that we need to know the differences between these two terms. First, like extinction is a 2D information. That means even if we have a 3D mapping of the extinction, each value tells us what happens from us to that point. While the dust density tells us actually the local property of the variation of the ISM. There have been a lot of work focusing on mapping the dust and extinction in 3D, and most of the works, what they do is usually treating each line of sight completely individually. That means there is no information coming from the neighboring lines of sight. And some recent work, what they have done is that after getting these extinctions per line of sight, you can get the derivative of the extinction, and that tells you something about the more local property of the extinction. And then they apply a post-processing smoothing kernel to get a better structure and get rid of some of the artifacts that produce with their map. But what we do is we take into account the full 3D neighboring correlations. That means we have a full 3D inference for the dust density. So we use the distance and extinction to stars in 3 dimensions as our input data, and then we take into account the 3D neighboring correlation. And we also consider the distance and extinction uncertainties. That means we do not need to cut on the quality of the data, because we know that that can produce a lot of biases. As an example, if one cuts on the parallax uncertainty towards Orion and look at everything after 500 parsec, you see that you can see structures of the Orion, because you start losing stars where you're actually interested in. Like where it's dusty, it's going to be a lot more noise in the data. And if you cut on the data noise, you're going to lose the information where you're actually interested in. So we do not cut on the uncertainty, nor in the parallax or in the photometry. Instead, we take into account all these uncertainties in our model, and this allows us to build a robust 3D dust map without any artifacts. Now, with this, we can study the distance and structures of the molecular clouds, and in particular, like Orion. Very briefly, how the method works. So we have observations to stars in 3D in different positions. So we have the distance and the extinction, and then we divide the line of sight to stars in the small 1D cells, and then we model the observed extinction to be the sum of these dust densities. So G here is the size of the cell, and rho is the corresponding density in each cell. So we have one of these equations per line of sight, and in order to solve this, we have to connect all these cells in the 3D space, and we do that with a Gaussian process. So the Gaussian process connects all the cells in 3D space, and the whole Gaussian process is defined by its covariance function, and here is how the function looks like. It tells us the closer to points in the 3D space, the more correlated they are, and if they're further away, they are less and less correlated, and at some point they are not correlated anymore. With this, we can connect all these points in 3D, And this allows us to find the dust density at any arbitrary points, even along the line of sight that were not observed before. And we calculate the full probability distribution function of dust densities for each point. That means we have the mean and the standard deviation of the dust density for any arbitrary point in the 3D space, and taking into account both distance and extinction uncertainties. Now, for this work on Orion, we use data from Gaia DR2 to get the positions of stars in 3D. And then we use the cross-match of Gaia with 2MASS and WISE already from archive of Gaia. And if we have these 2MASS and WISE bands, we can get the extinction from a method like RICE. And very briefly, how RICE method works. If you look at the colors of stars in different bands, you see in the middle right panel, the H minus 4.5 distribution is very narrow in the intrinsic color. And if we observe these colors, the difference between these observed and the intrinsic color is due to the extinction in front of between us and the star. And this allows us to calculate the extinction. So having these extinctions, we can find the redden color magnitude diagram. And that's where we start cutting on the data and have our final selection based on the physical space of the stars. Here is one example of how we do it. So here is the color magnitude diagram. And in color, you see the stars with the extinction calculated from RICE method. And in the gray, you see the theoretical isochrones from Padova models. And here in the sub-panel, we can see that there is a deviation. Some stars are like in the non-physical part of the color magnitude diagram. And those are the stars that we cut and we don't use them. And this is the final sample that we get, that we use as our input data. So now going to Orion, here you see a zoom-in version of the Orion towards the Orion A and Kappa Orionis. And I focus on two particular lines of sight. One is above Orion A, and the other one is in the middle of Kappa Orionis. First, if you look at the Orion A, so I'm going to show you the distance and dust density. So if you see a bump in this cloud, that means you are seeing where the cloud exists. And for this line of sight towards Orion A, we see some sort of a double peak. So we think that there is a foreground cloud to Orion A that was not reported before, although there are some works that are reporting on some young populations in front of Orion A that could be corresponding to this first bump. Now, if we go towards Kappa Orionis, we see this shell around this line of sight too that was thought to be associated with the Kappa Orionis star. Now, if you look at the distribution, we see the main cloud is at around 400 parsec, but from the literature, the parallax to Kappa Orionis star shows that it's at around 200 parsec. And this is puzzling because now we don't see any dust appearing at that point. And since Kappa Orionis star is too bright, it's not observed with Gaia. So it could be that either the parallax was not right or this dust is not associated with that star. And actually, there is an intensive work on this with Juan Soler and his student Ru that are working on the magnetic field towards this very interesting region, and they want to figure out how the dust and gas and the magnetic fields are related. And I will refer you to Juan's talk tomorrow that will talk more about the magnetic field towards this prototypical object. And this brings me to my conclusion that we actually find the foreground cloud to Orion A at around 350 parsec. And also we find the distance to Kappa Orionis to be at about 400 parsec. That is in contrast to 200 parsec Hipparcos distance. And this suggests that the Kappa Orionis ring could be actually connected to the tail of Orion A rather than being structures in front of Orion. Yeah, thank you.
Yeah, thank you. We switch to this view here. Yeah, thanks for a very nice talk. I do not see questions on YouTube at the moment. Do we have local questions here? There's one. Where's the... Yeah, maybe we start with a local question here, while the other questions are still loading. I see them coming in now. Excellent. Okay.
Okay. Hi, Sarah.
Hey.
So I have actually two questions. Am I allowed to ask two?
Sure.
Okay. So the first question is related to the foreground cloud to Orion A, because you just showed results towards one line of sight. So I was wondering if you also checked other lines of sight. And also, it looks like there is a double peak, but could that be just the extent of the cloud along the line of sight? And the second question is how likely is it that the Hipparchus parallax is wrong and of Kappa Orionis?
Okay. So for the first questions, yeah, I'm actually at the moment looking at trying to map the whole region in 3D. So it's almost about to finish, and so the thing is that I have a correlation length of about like 40 parsec, and the cell sizes of about like 10 parsec. So if there is anything within a 10 parsec circle, they will be all very highly correlated. So I would say that this cloud, if I still don't have the plot here, but when I look at the 3D distribution of part of this that is done, I could see that this is like some sort of a foreground cloud, but also connected to the main cloud. So I don't see like an actual division between two clouds, but it could be some sort of a continuous distribution, but the dust density actually drops a little bit and then goes up again. So that's something I'm still looking at. And for your other questions, I actually don't know. So the Hipparchus parallax shows the very, very small uncertainty. So that shows it should be pretty like robust, but it's pretty puzzling that there is no dust around that distance. So I don't know, maybe in the last release of Gaia VR4 or something, we could have some clues. I actually don't know.
Yeah, thank you. We had one question online, and I will read it out to you by Jan Orkis. Do you have any estimate of the relative masses of the clouds at 350 and 400 parsec towards Orion A?
So that's something that I haven't looked into, but there is a main problem that is, so when we are looking at these, when I'm building this map, I'm using data from Gaia. And since Gaia is in optical, we are actually losing a lot of stars that are in the very dense parts of Orion. So we would, in principle, underestimate the amount of dust, especially as we go further away. So I think towards Orion A already, if you look at the bump, I expect to see a sharper bump or like larger density at Orion A that I don't see. And I assume that's because the stars are like, it's so dusty that the stars are faint and they are not observed. They don't exist in the Gaia when the extinction goes high. So I think we are underestimating, I don't have any number at the moment, but even if we calculate that, I think we would some sort of figure out how we can take into account the underestimation that is caused by the extinction and the optical Gaia. But we can also, we are planning to see what we can see from gas and some sort of correlation between these two to see if we can get an estimate for the mass.
Excellent. Okay, we have one more question here locally from the audience. Yeah, should be high. By Joao.
Hi, Sarah. Thanks for the nice talk. I didn't understand how you get to conclusion 2, because you said that the distance is 200 for kappa. What was the argument to say that it's now 400?
So the parallax distance to the Kappa Orionis star from Hipparchus shows that this star is at 200 parsec. But when you look at the 2D map from Planck, you see this shell around Kappa Orionis, and it was assumed that this shell is produced by the Kappa Orionis star. But so that means we should see some dust around this distance to Kappa Orionis. But when you look at the dust distribution towards that line of sight, we do not see dust at 200 parsec. So
I have one just simple point, which is there's a new paper on cloud distances by Catherine Zucker, where I think you should read it because I might be making a mistake. I think there's no ring. There's a overlap of clouds at several distances. So the northern part of the ring is further back than the front of the ring. So there might be no ring after all.
Exactly. So that could be an explanation that is also consistent with the work you guys were doing that shows like this variation in the distance to Orion A, and the tail is further away. So that could be that this part is completely back and the other part is completely in front. And also we see some sort of complex structures in the magnetic field that could also relate to that. That's correct.
Okay. Yeah. Thank you. Thanks again for a very nice talk, also from us here in Leiden. We can continue any discussion in the YouTube chat window. We are out of time for direct questions now. But yeah, thanks again for your talk.
Thank you.
Okay, I will now switch on the screen, and we will go to our next presentation by Carolina Kubiak, who is based in Portugal now, and we will connect her to the session. She's actually here in Leiden with us, and it will just take a second to set this up. Carolina, can you share your screen?
Yeah, I'm trying, but it doesn't really work so well. Okay. Yeah. Screen. This one, and going here. Okay, does it work now? And can you hear me? That's the most important question, probably. So, first of all, thank you for hosting me today and for organizing yet another meeting about Orion. So I will try briefly summarize what I did as my PhD thesis when I was still in Vienna, and I was working on something that we called as an Orion belt population. The full motivation for my PhD thesis and the survey we did was to try to figure out what can be or what is the Orion OB population 1b, defined many years ago by Adrian Blau. And since we know by then that there are significant evidence for the in-front population of stars in front of Orion ONC, we were wondering and asking ourselves, is this population located only in front of ONC or maybe extending up to the north? So my work was mostly in the region of Orion belt, so those beautiful free stars and a very prominent sky feature. So we pick up the region of 3 degrees around the Epsilon Ori, which is the middle star of Orion belt. And we were using mostly archival data, so only technically archival data, to identify the stellar population day. So our survey was not fully covered since we were using SDSS by that time, and we were limited to the day coverage of the sky. First thing what we did was to look for the overdensity of stars in this field. So we focus us on the 2 mass data because we have full coverage, and we performing kernel density estimation and producing density maps. We can identify some structures, which is well-known Sigma Ori clusters, which is very young, 1 to 2 mega years old cluster around Sigma Ori quadruple system. Then embedded NGC 2024, and something that has not been mentioned before in the literature or identified clearly in the literature was the overdensity around Epsilon Ori. We can see immediately that the coverage field, the dense overdensity is not uniform. It's substructure in a quite complex way. But by that time, we focus only on that, assuming that this may be one single stellar population. And when Gaia DR2 release provide us the parallaxes for our stars, we immediately can figure out that the probability density of parallaxes is not symmetrical. There is a bump, which then can be interpreted as a two peaks in the distance histogram. So those two peaks can mean that we see two different populations, or that we are missing the stars because our sample has been selected photometrically, so we reject some stars and they may fit here, or we can deal with two different populations. Sorry, went wrong. This direction. So in the end, we definitely cleared our sample, removing the foreground population, and we started to work with something that we call near and far population of OBP. Based on color magnitude diagrams, the foreground population is separate perfectly if we use absolute brightnesses from Gaia. Unfortunately, the far and near population, where we made the artificial cut at 390 parsecs, they don't separate so nicely. So it is not statistically significant, the difference between them. We performed few tests and none of them give us a conclusion that we can treat as separately as two population. So this spread can be still due to the mixing of population, but it can be due to the binarity of the sample, due to the variability of the sample, or it can be just an intrinsic spread in the sample, in the properties of the sample. It looks slightly better when we take into account the proper motions, although it is still not statistically significant because green points are everywhere. So the far population is everywhere, even behind the blue things here. So we also investigate how this looks like in the spatial positions, and it is giving us some evidence that the farther population is slightly more centered and more clumped, if we can call it like that. So we cannot give a final conclusion what we are dealing with, either two population or some kind of contamination from different properties of the star. The next thing what we did was to investigate the properties of the sources itself. So we extend our survey adding a more long wave photometry. So here I'm presenting the photometry up to W4, but we were also trying to obtain as much as we can from the literature from other different surveys, but those were single sources. We then performed the spectral index analysis, so we calculate the spectral index for all of those sources for which we have enough data, and the distribution of the spectral index looks like that. We may deal with some disks in the population. Although those should not be supermassive disks and more like a 8th stage of stellar evolution. Therefore, we, using the data we have, so a lot of photometric measurements plus new Gaia data, we use the models provided by Robitaille and perform the SED modeling. Out of this modeling and the whole approach that Tom is using in his new paper, we estimated the properties of the central source and of the disk if the disk was present. We are pretty certain about the properties of the central source because they are pretty well covered by the Pan-STAR right now and the TUMAS surveys. The disk properties are still under a huge discussion because we can see there is quite degeneracy in the models. So that's another example. So then the next step here to perform more of the SED modeling will be to apply for some longer wavelength data sets, and Sophia deadline is coming soon. So that's definitely next step here. Then we moved with our investigation to the variability, because young sources assumed supposed to be variable. So based on mid-infrared variability in W1 and W2 multi-epoch photometry, we identify 81 candidates, more coffee needed, for the variable stars, for which we investigate the light curves in both epochs of the observation, and we can see different patterns. Some of them should be related to the presence of the disk and changing of the geometry of the system, but some of them are or can be interpreted as just an imprint of stellar activity. What is the most important conclusions for us right now is that variability can cause us a misclassification of the sources. If we catch the source in a different phase of variability, we can fit a different SED to it or the different alpha slope. Therefore, we can classify the source wrongly or misclassify it. And since it is always significant numbers of stars, for my sample, it's almost 13% of stars that are suspect of strong variability, we can, then our observables like star forming rate can be wrong or can be just derived wrongly. So as a super fast conclusions, I would leave this page and saying what we did as a three points, sorry. So we definitely use Gaia DR2 to clean our sample, but also to estimate the size of the cluster itself, which right now, based on the Gaia data, we can say the sample is as long as 60 parsec along the signs of line of sight. We know it's not homogeneously distributed in space, and the group seems to have slightly different spatial motions. Based on the SED modeling, we know those are mostly low mass M stars with the low mass passive disks. And then optical and near mid infrared variability shows that there is a significant numbers of variable stars in the sample. And that would be all.
Okay.
Hope I'm okay.
Thanks for your help. All right. I see we have a couple of questions here, and I will start with one by Sirk. In the beginning of your talk, you were discussing clustering. What kind of clustering tests did you use to compare these data sets?
So at the very beginning, you mean when we did the KDE distribution? Few slides ahead. That's not much of them. Yeah, here. Okay. So we didn't perform clustering tests per se. I was just testing are the difference between those two samples statistically significant. So on the distance distribution, we just test the standard statistical tests like KS test, fitting the regression, and comparing the errors of that. Here we tried to play with two sides statistical tests to compare the distributions of the samples, but they were also producing us not a straight conclusion, so they were not distinguishing those two samples.
There's another question here. This is from Alvaro. What is the fraction of sources with infrared excess as an indicator of youth?
So when we use all-wise photometry, more than 400 sources are indicated as having a slope that is not indicating it's a naked photosphere. So more than 400. I have the numbers exactly. This is correct.
Okay, it looks like we also have one comment by Marina Kunkel. Two populations do have pretty distinct radial velocities, more so than any other dimension of the phase space.
So can you repeat?
The two populations do have pretty distinct radial velocities, more so than any other dimension of the phase space.
Yes, but if I compare my sample with this, what Marina presented in her paper, I'm not finding any common sources. So maybe this that we are still not sensitive to the same stars. I also compared our results with the survey performed by Cesar Briceño. We then are getting about 10-15% of the common sources, and the conclusion is the same, that the spread on the velocities they are getting is pretty large, that we cannot say is it one or two different populations. The sources mixed pretty well.
Okay. Yeah, I think that concludes our discussion. Again, you feel free to continue the discussion in the Q&A on the YouTube page, and let's thank Carolina again for her talk. Excellent. And we switch to the next speaker, who is also connecting from Leiden. He's we just wait for him to set him back. So his name is Bokan Chen.
Hi.
And he will discuss discovering new stellar populations in Orion with Gaia DR2. So if you could share your screen.
Oh.
And then we are ready to go. And again, feel free to continue the discussion online at the Q&A on the YouTube page. As we get ready here. Okay, so we should be good to go. Please go ahead.
It's not projecting. Does it still work?
Yes.
Okay. The bottom's missing a little bit. Not sure why. Okay. It's nice to be here. Today we'll talk about discovery new stellar groups in the Orion star forming complex with the unsupervised learning. So first talk about the goal here. So Gaia DR2 has many more stars available in the Orion complex. So the question is, can we identify stellar populations, especially new ones, based on 5D phase information provided by Gaia DR2? So which 5D we're talking about here? So position in the sky, Orion deck, and parallax, and pulse motions in both directions. So there's a note here. So we're not using radial velocity here just because it's very limited. So we're imposing some selection criteria for the Orion complex. So here are the criteria directly from Kuko et al., 2018. So RA is really limited between 75 and 90 degrees. Dex between -11 and 15, parallax 2 to 5, and both pulse motions from -4 to 4. And in addition to that, we are imposing a quality cut from Gaia using a renormalized unit weight error, RUWE, less than 1.4. That information available from Gaia technical notes. So in total, we got 29,030 stars, and this will be our sample for this study. So before we go into methodology, there are two acronyms here we're going to use over and over again. The first one is dbScan. It stands for density-based spatial clustering of applications with noise. And the second one is SNN, stands for share nearest neighbor. And SNN is basically an extended version of dbScan. First we're going to talk about dbScan. So dbScan is a very simple idea. So we have two parameters, and that translates into a single density threshold. So the first one is epsilon, and that's the initial search radius And the second one is the mean samples. That stands for minimum number of samples. So you can sort of think of this as population density. So if you fix the radius around your house, say 1 kilometer, the more neighbors you have, the higher the density is in your neighborhood. And same thing, we can fix the number of neighbors. If you need to go a very long distance to find a certain number of neighbors, then you probably don't live in a very dense neighborhood. So you can see that in the diagram here, we have very high density that corresponds to small epsilon and large mean samples. And then we also have aligned, this corresponds to low density, and that represents large epsilon and small mean samples. So basically, imagine you have a knife, you cut across the diagram, and the leftover discrete parts are your clusters. So you need to find the optimal density because you can only have one density threshold here. And of course, we have a problem, and the problem is it's not always easy or possible to find there are multiple density, especially when there are multiple density peaks, and they correspond to very different densities. So here's like a simple 2D example here. There on the left panel here, you have cluster A and cluster B. Cluster A is much denser than cluster B, and they sort of overlap. If we pick a very high density threshold in the middle here, you can see we recover cluster A very well, but we completely missed cluster B. But then if we lower the density threshold, we can recover cluster A and parts of cluster B, but they sort of merge together, and it's very difficult to separate them. So here's SNN to the rescue. So to overcome it, we introduced a new distance metric called the Jacquard distance. I didn't invent it. It's just available from the web, from online. So here, for every star, we generate a list of neighbors with similar properties in our 5D space. And when it comes to how to get the stars with similar properties, I'll discuss that later. So here's the definition of Jacquard distance between two stars A and B is 1 minus the ratio of the size of intersection between A and B over the size of union between A and B. So here you can see the improvement on the new panel over here. Using SNN, we can clearly separate A and B. Of course, in the outlier region, SNN still has limitations, but it's a huge improvement over dbScan from before. So now we're going to talk about similar properties, like how we're actually going to get that in the 5D space with different ranges of parameters that represent different physical properties. So let's go back to the 5 parameters over here. So we're going to convert the first 3 spatial related parameters into rectangular x, y, and z. And then we're going to separate the 5 parameters into 2 groups. So x, y, and z represent spatial coordinates. And then we have proper motion that represents kinematics. So here's the procedure. So we're going to start with the x, y, z first. We're going to get nearest neighbors in x, y, and z. And then once we get the nearest neighbors in spatial coordinates, we're going to only keep those that also share similar proper motions. And we're going to use another parameter to control that. That's the d proper motion. So after we got the nearest neighbors for every single star in 5D space, we calculate the distance matrix. And with the distance matrix, we can perform the dbScan clustering. And of course, we're going to use our own friends here, the epsilon and mean samples parameters. So in case you haven't noticed, we still need to find that one perfect set of parameters if we just follow through. So instead of doing that, I'm going to actually randomly generate 2,000 set of parameters within some range. And instead of using the one set of parameters, we're going to identify the most repeated groups from these 2,000 sets as our final results. So here, when I generated random parameters, we're actually fixing epsilon mean samples. And this is basically to reduce the computation time because they simply do not do much for our exploratory analysis. So there are very many benefits on doing this procedure. So the first one is we're not bound to one configuration in 5D space anymore. We can have a group that may have a larger spread in proper motion and a smaller spread in spatial coordinates, but then we can also have the opposite. So the second benefit is here, we're also getting a measure of stability relative to parameter values. If a group is repeating over and over again, then they must be a very stable group. And the third benefit here is also getting some measure of membership probability here. So if a star repeats in a group over and over again, then that star has a very high chance of being belonging to the group. So what do the groups look like coming out of the algorithm? So here I'm showing the first 9 groups in 3 separate projections. So the leftmost projection here is simply projecting onto the sky, Orion deck. And the middle here, I'm projecting the groups onto parallax in the x-axis, and then declination on the y-axis. And then the third last projection here is simply the proper motion. So I'll also label the groups here in proper motion space. So the first group here is just a group just below lambda Orion. And then, of course, this green group here corresponds to 9. So the 9th group here is lambda Orion. And we also have, in the south here, we also have NGC 1980. And we also have the tailed Orion Nebula cluster. Some of these groups, of course, I already mentioned and discovered before. Here I'm going to point out like a few new ones. So the first one and second one, there are new groups that have not been discovered before. So this algorithm can recover groups that we've seen before and the new groups. And one thing to point out here, if you look at the blue group here in the south, in 1980, you can see in the parallax, most of the stars actually have parallax larger than 2.5. However, after we move the group, so here we're showing the stars after we moved all the stars assigned to a group. So you see here, if we select some of the stars just in the same region but not picked up by the algorithm, the parallax of these stars actually slightly smaller, so they're actually further away. So what we're picking up here, back to N1980 here, is actually the foreground population in the Orion Nebula region. So in total, we actually have 32 groups. So here shows the rest of the groups. Of course, there are too many groups here to go into in this talk. But one thing I'll point out here is the orange group. So if you look at the orange group here, they have a much shorter distance to us. It actually corresponds to Orion X population that's been discovered before. And here, can you see the print pointer? Oh, it's
Can you go to the screen quickly? To the
yes.
You can now go to your presentation and put it in.
Present. It's not.
Yep. No.
Okay. Can you see the printer now? Okay. I guess. Yeah. So here the green group was pointing out here, that has a much larger parallax, and that actually corresponds to a population that's been discovered before called the Orion X. Similarly, in the south here, you can see there's a stream of stars, and that corresponds to the Witch Hat Nebula that, of course, has been discovered before. So here we're just going to have a brief conclusion here. So by improving a common clustering algorithm, we're actually able to identify previously discovered and new stellar groups in the Orion complex. Of course, these groups will help us better understand the formation scenario of the Orion complex, and we're still working on it. Some of the next steps we're going to perform are first, age estimation using base 9 algorithm, and second, we can study the chemical abundances from Galah and Apogee, and also the referee suggested we should incorporate measurement errors, and we'll be working on that. And in the future, of course, we'll hope to include the missing dimension here, the radial velocity, as well as the better data from Gaia DR3. And with that, thank you for your attention, and I'll take questions.
Excellent. Yeah, I see at least one question here online. That's a question by Paula. How do you account for outliers when you search for nearest neighbors in the 5D space?
Go back to the presentation. Okay. So this one is actually, because we're using dbScan, and dbScan allows the removal of the noise stars. So when we're actually, so here, the last step here is the dbScan clustering. So as long as we select the epsilon and min samples, some of the noise stars will still get removed. So we're not removing outliers during the nearest neighbor selection phase. We're removing them in the clustering phase.
Okay. And I see a second question here by Yannis Kos. The Hertzsprung-Russell diagram is good for finding outliers that lie on the main sequence. Did you make any HRDs?
So I have made a few, but I at this point not ready to include them in the presentation yet. I think after we actually estimated the ages, we can then plot the HR diagram.
Excellent.
Yeah.
Okay. Are there any more questions here locally? Okay, so that concludes the discussion for this talk. Thanks again for your talk. And,
thank you.
Okay, we'll actually switch over to another talk locally. This is now a brief chance to see two pseudonyms in the stream. I'm not Orion, my name is Jan, and this is not Stefan Meingast, but our next speaker, Christine, who is based in Vienna, and she will talk about multiplicity in Orion A. So I will just get her presentation onto the stream.
Oh, hello, do you hear me?
Yes.
Okay. Yeah, my name is Christine Ackerl. I'm based in Vienna, where I currently finish my master thesis in the group of João Alves. And I'd like to thank the organizers for letting me present my work here. I especially appreciate to talk in front of people who actually know how awesome Orion is, and I don't have to explain it to them. But I guess a few of you are not as aware as you should be how awesome Orion is for multiplicity. And if you now think, okay, I don't really care so much about multiplicity, my answer is you should. Of course, we know that almost 50% of solar-like field stars are part of multiple systems, and even more with the higher stars. And we've heard it before today a couple of times, a lot actually, that binaries are important and binaries can change results and have an influence. So if we deal with stars, we always have to also deal with multiples. A second very important thing about multiplicity is that it can, of course, also reveal some information about star formation mechanisms that lead to the multiplicity properties. So the problem is, of course, if we want to understand stellar multiplicity, we have to go back to the original multiplicity properties of stars, so to the very young stars. With this, it has been a problem so far that we are limited to small sample sizes, which of course lead to bad statistics, and the small samples in different star forming regions are very hard to compare. So the solution for this is Orion A. You all know probably that it's the nearest massive star forming cloud, and it has very many advantages when it comes to multiplicity, because we have these different environments here where we can compare our results. So we have very dense regions, dense clusters, and also very loose associations and very isolated star forming events, and all in one single star forming cloud. So this makes it very easy to compare results from different environments. A second, we also have different evolutionary stages of YSOs here, which I will point out later. And the most important thing, we have thousands of YSOs, so a very large sample of young stellar objects that we can investigate. So the sample we were using for this work mainly comes from Josefa Großschädel's work. She will give a talk tomorrow. And she basically refined and refined the previous catalogs of Tom McGeth, for example. And we also use the work of Piliteri et al. And from him, we used class resources. So in total, we have 152 protostars, 162 flat spectrum sources, and 2,617 pre-main sequence stars with disks from Josefa Großschädel's work, and 455 class resources. The data, the image data we are using comes from the Vienna survey in Orion, or Vision, which was done by Stefan Meingast et al. We'll give a talk later and talk a little bit about this too. So we're using near-infrared data from the Vista telescope, more precise JAH and KS photometry, which is, of course, seeing limited ground base. So the resolution limit is about 0.6 arc seconds. And it covers the whole Orion A cloud. So how do we estimate the multiplicity properties of Orion A? As I said, we only have image data, so there is no spectroscopy, no proper motions. So we only can look for companions that appear like companions. Of course, we do not know in the beginning if they are some. So first of all, we look at each single YSO, do PSF fitting and PSF subtraction, and hopefully in the end are left with something that we can identify as a companion candidate. As I said, we don't really know if this is really a companion or not. It just appears as a companion, but I'll come to that later. So this seems very easy, basically just counting stars, but of course it brings a lot of problems with it. First of all, due to the large sample size, it's hard to, or nearly impossible to do visual examination. So we have to invent a fully automated PSF subtraction and companion detection routine, and also make sure that it doesn't detect any false positives. We did this by using a test sample by Marina Kunkel et al. So we trimmed our companion detection routine to get the best results for this sample. It turns out that, sadly, we have to exclude some very problematic sources, which are either saturated or have high background noise or just in very crowded areas. And this also led to the exclusion of the ONC itself, unfortunately. So the final target YSO sample size is 1,851. So how do we find out the number of companions now? Of course, we also have to take care of the line of sight coincidences. So if you plot just the number of companion candidates versus the separation in arc seconds, and then divide them by the area, you can see that there is this flat region here where apparently the background contamination or the number of companions stays constant. So we can assume that this is the background contamination and just take this part and subtract it from the sample of companion candidates. If we go back to the total number of companions, then we see that we are left with these excess companions here, which are apparently real companions compared to the background contamination. So this area is approximately 0.625 arc seconds wide. And when we subtract the contamination from these companion candidates here, we are left with 86.5 companions to 1,851 targets. So this leaves a companion fraction of 4.7%, which is a very lower limit. The problem with this is that we estimated the contamination much less strict than we estimated the companion candidates. So we we subtract too much contamination at the moment. I'm currently working on this. So just that you take into account that this is only a lower limit for the result. Okay, so we can also look, of course, at different samples now. So, for example, different environments. And Josefa Groschel, for example, found that that there is a good reason to divide Orion A into two parts, which we can, for simplicity, call the head here with the ONC and the tail here. And if you just look at the different samples in these environments and also the different evolutionary stages of YSOs, we get this result. So here we have the protostars in the tail, the flat spectrum sources in the tail, the disk sources in the tail, the class 3 sources, and the total number of sources in the tail, excluding the class 3 sources, just because we saw that it is probably not as consistent as it should be if we include the class 3 sources, also because we are not sure if they are exactly at the same distance. On the other hand, the head, the protostars here, flat spectrum sources, disk sources, and class 3 sources. So what we see here is, first of all, that we have a higher companion frequency in the tail of Orion A. So the points here overall are higher up than here. And we also see a very clear dependence on evolutionary stage. So the companion fraction decreases with age. For comparison, this is the what we expect for the main sequence. This is what we would expect for Taurus, for example. So as I told you, these values are just a lower estimate, so probably they will all shift up. So the takeaway points, Orion A is a perfect playground for multiplicity people. There is a lot more to do, of course, with this sample and with this data. Multiplicity strongly depends on evolutionary stage. So we really see this decrease with age in both parts of the cloud. And multiplicity also depends on environment, because we really see that there are less multiples in the head, in the denser region of Orion A, than in the less dense region. So I'm open for questions.
Yeah, thank you. I already see one first question online here by Paula. Can you estimate the companion fraction as a function of mass?
Currently not, because I also don't have any mass estimates. I could, of course, do this as a function of magnitudes, but I haven't done it so far.
Mm-hmm. Okay, we have another local question here by Alvaro.
Yeah. Hi. Yeah, we almost see us here. So do you see a difference between the close and wide binaries? So do you see a gap in between, or is it a continuous distribution?
I do see differences. So if you look at some distinct samples, you see that you have kind of a second bump, so at the wider binaries. But there is still, I still have to do some statistical tests with this, so I can't say anything about this right now.
Thank you. All right. Oh, we have another question locally. I don't know that.
So I'm probably very ignorant about this, but why does multiplicity depend on age?
On age? Because the idea is that the binaries get disrupted after a certain amount of time, because we have interactions with other stars. So the probability that the binary stars or binary system is destroyed is higher with age.
Okay. Even if the environment is not dense?
Apparently.
Okay.
That's the point, and that's the question, yeah.
Yeah, okay. Thanks.
Okay. I don't see it yet. There are rumors there's another question. I have to wait for a few seconds until it shows up here. Ah, there it is. A question by Marina. How well characterized is the completion of detection of companions?
Sorry, can you?
Oh, I guess, so how well characterized is the detection completeness of the companions?
The completeness is how well characterized, yeah. So the one thing is that we can compare with Marina's sample, for example. So we see how many of her stars we find, of her binaries we find. I do have a slide on this, which looks very not so good, but so this, for example, is are the binaries in her sample, separation versus magnitude difference. The red ones are all we miss, and the blue ones are the ones we detect. So this is one way to determine the completeness. The other way is by adding fake stars and doing the analysis with fake stars again. But I haven't done it so far.
Mm-hmm. Okay. Thank you. Are there any other questions? Any rumors of questions? Okay.
Just a small question. I think in the plot where you show the difference in environment, yes. I don't think your data are consistent with any difference in environment, but the hypothesis would make sense. So I don't know what's going on, but actually they're consistent with the error bars.
You mean they are consistent with the error bars?
Huh? Sorry?
I didn't understand the question. Was it a question?
Yeah, these are not actually, no, it's a comment, sorry. These two samples are consistent. They're not different.
Yes, within the error, yes. That might be true, but also the error
is true.
Yes.
But anyway, but the hypothesis makes sense.
Yeah.
But it's not borne out by these plots.
Yeah, but also the data is not complete yet. So I mean,
yeah, lower limits.
Yeah,
got it. Cool. Thanks.
Okay, and there's another question locally.
I guess the question is: have you thought about just coming at this from a theoretical perspective and trying to work out, whether you expect the timescales that you're looking at with the densities that you have, the separations you have, you can figure out a characteristic timescale for an interaction. So you can figure out whether these are consistent with the theoretical interaction time. Is that something you thought about doing?
I didn't do that yet. I mean, of course, this has to be compared with simulations.
You don't need to do simulations. You can just there's analytic expressions you have, just like Vienna or something like that. You can just do an analytic calculation.
Yeah.
Figure it out. The other thing would be then if it's not consistent, then you could work out whether it might be consistent with a dynamic interaction within the multiple system. So if you have a chaotic interaction over time, whether that might be something that's more practical for this, because then it would make sense with the independence of the environment, but the correlation with time in the low density regions. And then you just need to work out what the restrictions are on your data set, like what's the closest binaries that you have, whether they're consistent with kind of dynamic interaction or triple system or higher order.
Thanks for the comment. Yeah. Maybe we can talk later.
Yeah. Cool. Excellent. Yeah, thanks again for your talk. And last speaker of this session is the real Stefan Meingas. We'll just wait a second for the screen to be set up. So Stefan is going to talk about infrared extinction in Orion. And there we go.
Thank you, Jan. So also I want to start by thanking the organizers for this opportunity to present this work. So this is actually a project that we did more than 2 years ago, and we published last year together with Marco Lombardi and João Alves. And as Christina before, I was using a data set that we've been working on for a few years now. It's the vision data set. And so I want to add two things here. One thing is that if you are working on Orion A and you're using 2-mass data, then I would recommend not using 2-mass data anymore. I would actually recommend using our Vista service. So 2-mass is incorporated into this, so you're not losing the bright end. So please use this data. It's very well tested already. And the second comment I want to make here is that for the infrared extinction study that we did, we also used pan-stars data and Spitzer data. So we cover a wavelength range from about 1 to 25 micrometers. Good. So the project that we were looking into was determining properties and characteristics of the extinction law, of the infrared extinction law, actually. And the idea behind this was that when you look into literature results on determination of the extinction law, so the amount of extinction as a function of wavelength, then most of these studies actually use sightlines toward the galactic center or the galactic plane. So for instance, the coal sack is a very popular target. And the idea there was then that when you look toward these sightlines, then you might be biased by multiple overlapping components along the line of sight, which have different temperatures, different densities, and so on. So it's very hard to control systematic effects. And here the idea was then to use Orion A as a template, because Orion A is presumably very isolated as a cloud, is off the plane, comes with other systematic errors, for instance, that you can't use the same techniques to determine the extinction law as you do them toward the galactic center. And the questions we asked were, for instance, if there is a universal near-infrared extinction law, so this portion, whether this changes with an environment or with density, or whether we find extinction law differences across the face of the cloud. And if we do find extinction law differences across the face of the cloud, where do they come from? So can we tie them down to dust grain properties, perhaps the size of the dust grains, or does maybe the feedback from the hot stars in the Orion Nebula cluster impact the dust grain properties? How do we do this? So since we're using this extensive photometric data set, we constructed a series of color-color diagrams. And you see here on the right, you see a so-called control field, so a field without any extinction in various combinations of colors. And you see the same combination of colors on the left here. And this is then the Orion field, the Orion A field. And you can nicely see that the extinction actually scatters sources along the extinction vector. And to characterize the extinction, we use this beta parameter, which is essentially the slope in the color-color diagram. And this slope is also directly proportional to the extinction ratio. So you fix your amount of extinction at a certain wavelength, then the measured slope gives you the extinction ratio. So we use this as a proxy to study the extinction law in Orion A. And another thing that we did was when you look at the cloud in projection and you color it with measured temperature from dust emission measurements, you actually see there are differences in the environment, being so that in the western parts of the region you have the cluster with a tendency of warmer dust, and you have very cool parts in the east. So we also divided this to first order in 2 regions, and using the same names that later Josef gave these 2 regions, we call the region that contains the cluster the head of the cloud, and the other region the tail. So this is also color-coded in blue then later, and the tail is color-coded in orange. So there are these differences across the face of the clouds in temperature. And now what we did, we calculated this beta parameter, and you can see here a diagram of this beta value, or transformed then into an extinction ratio as a function of wave number, or up here the wavelength. And these are the measurements we did for the entire cloud. And to prove that this actually does make some sense, here are a couple of models that you can use. Most prominently, perhaps, the Weingartner-Drain models. So there is a nice fit already going on when you look at the measurements for for the entire cloud. And you can zoom in also here on the near-infrared portion and in the mid-infrared portion. You see that there is a flat mid-infrared extinction law. And now in the next slide, I'm going to split the measurements up in this head and in this tail portion. And what we find there is that there is actually a systematic trend. So you see a systematic difference here in the mid-infrared portion and also in the near-infrared portion. And then the question we asked was, where does this come from? So perhaps we can make a zero-order argument saying that this is a result of different grain sizes. And this was a bit unfortunate. So the answer is unfortunately not as exciting, because we compared this to models. And when you stay, for instance, within the Weingartner and Rain models, so if you look here at the black lines and the gray lines, you see there is this offset between the dashed black line and the solid black line. And the main difference between these two models is that the lower line here uses very, very large dust grains. So you could argue, just to reproduce the mid-infrared extinction law, you need overall larger dust grain sizes. Or in other terms, to also reproduce this offset you see between the blue and the orange dots, you also need an increase in dust grain sizes. The problem then is that if you take into account other models, for instance, by model published by Nikolai Voshchinikov in 2017, they also nicely reproduce this flat portion of the mid-infrared extinction law, but they don't need any large grain sizes. So everything is below 1 micrometer or so. So this was a bit disappointing then in the end, that we could not make any conclusion on dust grain sizes. So actually, looking then at this result, we started to dig a bit deeper. And here I color-coded again the clouds on the top right with temperatures. And then we subdivided the region into multiple subregions. And you see these beta parameters for different wavelengths, so for different pass bands, IREC, and here the H band in the infrared. You see these beta parameters then plotted for each of these regions. And essentially, when you go from left to right for these labels, you also go from the eastern region to the western region over here. And you see that there is this trend persisting in multiple bands. And another interesting comparison that you can do is that when you look at the 3D cloud orientation, that was actually only later published by Josefa, she will talk about it tomorrow, you can also see that there is a difference in distance between this portion of the cloud and the other portion. So meaning that L1641, so this eastern portion, actually sits in the background and doesn't actually see the more massive stars in the cluster. So this was our conclusion back then, that we do detect a variable infrared extinction law across the face of the cloud, but we were not able to tie down the physical origins of this trend that we find. So we are still, unfortunately, we have not continued this work yet. There was a lot of other things to do, especially with the Gaia data release. So I would be very happy to discuss this also in the unconference in the coming weeks. Perhaps you have some ideas to tie down the physical origin of this difference, perhaps also related to the ONC. And another thing that we surely have to do is we should definitely test this out in other nearby cloud complexes, perhaps most prominently Ophiuchus. And for that, I think I have another minute or so, I guess. I just want to present another project that we've been working on. So this vision project of Orion A was sort of a pilot study, and we are now extending this to a much larger survey that we call very originally Visions. So this is essentially doing the same thing, extended for other nearby clouds on much larger scales and also in multiple epochs. So essentially what you get is also then in the end proper motions for the embedded populations that Gaia is not able to see. We already had a data release this year, and the next data release is actually coming up early next year. So if you're looking into near infrared data and perhaps then later also not 2020, maybe 2021 or 22 for proper motions of embedded sources, then this is definitely the way to go. And with that, I think I go back to this slide, and I'm happy to take questions. Excellent.
Okay, we're going back here. Are there any questions? We have at least one local question already by Alvaro.
Yeah. Yeah, so Stefan, really spectacular results. So you explained the differences in terms of, or you try to explain them in terms of sizes.
Yes.
You try composition. So what happens if you have dust with ices around it? You change it, and it will explain a bit more the correlation with temperature, right? But
yes. So we played around with a lot of different setups for the models, but the problem is you're totally lost. So you cannot really explain this very small systematic difference that we find here with for instance, chemical composition. So you can play around with the composition. You do observe trends, but you cannot tie it down to, for instance, one specific chemical.
That would be
interesting. Yeah, it would be very interesting. And for me, the zero order result would be to go tie it to grain sizes. Even that was problematic, because if you come up with a different mathematical model for the dust grains, so Nikolai Multiplicity used porous dust grains. So essentially, they made fluffy grains. You can also explain this infrared extinction law, but you don't need large dust grains.
Mm-hmm. Thank you. Mm-hmm. I will maybe add a quick follow-up question to this. To what degree do you think does the emission data at various different wavelengths and, of course, scales to some degree help determining the origin of this?
So I think it would definitely help tying it down. And this was actually one project that I wanted to follow up with actually you. But unfortunately, we did not invest too much time into this project after we published this paper. But this is something that perhaps we can discuss.
Yeah, we should discuss. Cool. Excellent. Any more questions? Rumors of questions? Nothing there. Okay. Thanks again to Stefan, and yeah, thanks to all of you following this online. Thanks to all our speakers of this session. I think that's worth another round of applause. That was really a very nice set of talks. We will now have a traditional Dutch siesta here in Leiden. And while we are waiting for some of our speakers to wake up so that we don't have to call them at 4 a.m. And then we will continue in the afternoon with our next set of speakers. So see you in a few hours. Thanks again.